Now let us discuss about the motor efficiency, motor sizing and motor mass. The general idea is that whenever we would like to select a motor for electric vehicle application, what should be the parameters that must be considered while selecting a motor. So that is what we would like to discuss here as an introduction in this slide. So first and foremost criteria, let it be any application, whether it is an electric vehicle or for that matter any industrial or other application. The first criteria is that the motor chosen for the application should be as efficient as possible. So what is the meaning of as efficient as possible? The meaning is simply the efficiency should be very high. So as per the electrical standard, the efficiency of the motor lies in the range of 85% to 97-98%. So naturally we would like to have the efficiency in the higher 90s. Okay. Then secondly, the how to go for selecting such a motor. So we must know on what factor the motor efficiency depends on. So generally the motor becomes more efficient as their size increases. So the larger size motor tend to be more efficient as per the design specification, as per the design standards. Okay. Then the speed of the motor has the highest effect on the efficiency of the motor type. Okay. If you want to select a motor, then rather than whether the motor is a DC motor or induction motor or BLDC motor or SRM motor, the very first parameter that matters, that will decide the efficiency irrespective of the type, is the speed of the motor. Okay, because the speed of the motor decides the losses in the motor. We have seen earlier the equations while deriving the torque equation in case of a brushed DC motor, and we realized that the torque is proportional to the product of flux and current. So if the speed of the motor chosen, if the motor is a slow speed motor, naturally it will have a larger torque value. So the losses in the motor are proportional to the torque. Lower speed motor will have higher torque and hence it will have higher losses. So always be trained to select a motor which has higher speed for as far as the rating is concerned. Higher the speed, lower will be the torque, and naturally lower will be the losses. Losses mainly occur with the increase in torque, because torque is decided by the current. As the current circulates through the motor windings, the windings get heated up and the losses starts occurring. So what we want here is that the winding should be, or the motor should be cooled. So liquid cooling or air natural cooling is adopted in order to keep the temperatures low. So the effect of keeping the winding temperature low is that the resistance offered by the winding will be lesser. When the winding gets heated, it tends to offer more resistance and hence more losses occur. So if the motor is cool, naturally the efficiency can be improved, but of course the effect of cooling on the efficiency is limited to about 1%. Then further, the efficiency of electric motor that we actually get from a particular motor may be very different than what is given in the specification. The reason is simply because the specifications are the standard specifications and under standard operating conditions. So when we are using the motor in the electric vehicle application, it may not operate in an optimal manner. It has to undergo various operating modes, and we may get an overall efficiency which is slightly lower as compared to the standard specifications of the motor. Let us check with some interesting statistics to understand how the motor size and speed and efficiency are correlated. These statistics are statistics and graphs. These are about the motor efficiency and motor sizing. Please observe on the left hand side, this is the graph. It shows on y-axis is output torque in Newton meters, and x-axis it is the motor speed. So this is basically torque speed characteristics, and two sets of torque speed characteristics are indicated here. One is a 50 kilowatt intermittent operation. So this is the upper characteristics here, varying over a range of speed from 0 to 7500 rpm. And then secondly, below this, the second characteristics is a 30 kilowatt operation for continuous operation, 30 kilowatt output. So this is for 50 kilowatt but intermittent operation, so that means frequent start stop, reversal and all that. Okay, and then this one is for the continuous operation, lower one. So two different characteristics are here. The first one characteristics is that it indicates the variation of efficiency, okay, on a torque speed characteristics diagram. Apart from the torque speed characteristics, we can see here these contour diagrams are there. You can see this is a circular part. Okay, inside the circular part it is showing efficiency to be 94%. Similarly, this is another contour 92, then this is yet another contour 90. So this is the range of operating within this contour. For example, this one, this contour is for 94%. If we increase the operating area, then it becomes a 92% efficiency in this range. And if you further increase the operating area, if we go on moving away from this, so it's 90, then 88, like this. So in either case, for the continuous operation as well as this intermittent operation, the efficiency of the motor is also shown here. Please observe that the efficiency of motor for maximum torque. So here it is a maximum torque. This is a maximum torque, 225 Newton meter. The efficiency is lowest, having value of 82%, right? We can see it is 82% for a maximum torque that occurs during the starting. And as the motor picks up speed, so gradually with increase in speed, gradually the torque will decrease. And as I had already discussed, that torque decides the current and current decides the losses. So as the torque decreases, there is a gradual increase in the efficiency from 86, 88, 90, then 92. Okay, so this efficiency for intermittent operation maximum is goes up to 92% in this particular range from here to here. And if the speed increases further, so again we see that the efficiency starts decreasing. These are the values for the efficiency. Similarly, the maximum efficiency is possible for only the continuous operating mode. We can see that continuous operating mode only overlaps with a contour which has got an efficiency of 94%. This 94% area, it is not overlapping with the intermittent operation characteristics. So in this region, for continuous operation, we will be able to get nearly 94% efficiency. So that is quite obvious that if motor is running stably at one particular range of speed, neither high torque, neither too high speed, so it will give an optimum efficiency. The efficiency drops as we move away from this area, either towards a high torque low speed region, or we move towards high speed low torque region. But at high speed, the drop in the efficiency is not as drastic as that of a high torque. The torque affects the efficiency much more as compared to the speed. Now further, let us observe the table on the right hand side. Here there is a table on the right hand side bottom. It indicates two parameters. The left one is a power. This is a motor size. Size of the motor is indicated in terms of power rating kilowatt. So 1.1, 2.2, 4, 7.5, 15 and so on. And corresponding to this motor size, the minimum efficiency that will be available with the motor is indicated here as 83.8. So as the size of the motor goes on increasing from if we take a larger size motor, let us say if we move from 1.1 to 90 kilowatt, you see that the efficiency that will be available, it increases from 83 to 95. Just by having a larger capacity motor, we can have a better efficiency. And if we see 90 kilowatt motor and 95% efficiency, it is a huge saving in energy and availability of large amount of power. As compared to this one is 83%. So we observe that the size of the motor also affects the efficiency. Now let us check the effect of motor mass on the specific power and its impact on the choice of motor for the electric vehicle application. The mass of a motor is a crucial factor in deciding the overall weight of electric vehicle which it will drive. The range of EV can be extended if we use a lightweight motor at the same time having a higher speed rating. So for understanding this aspect, let us take a look at the characteristics shown here on the left hand side. You can observe this is the characteristics where on the y-axis you have specific power, that is motor rating in kilowatt per kilogram weight of motor, and on the x-axis we have the motor power in kilowatt. So this is specific power versus motor power rating. Okay, and on these characteristics three different combinations of operating ranges are indicated. First one is an induction motor, which is actually a two-pole and air-cooled type of induction motor. Then second combination is a switch reluctance motor and a BLDC motor, again air-cooled. So both these are air-cooled combinations, and the third one is a BLDC motor, which is water or oil-cooled. So please observe here the comparison. The lowest specific power is available with induction motor. You can see here the range for the specific power is lowest for the air-cooled induction motor, and it offers this specific power lying in the range of let us say around 0.05 to 0.15 kilowatt per kilogram over a wide range of power rating for the motor, right from 0.1 kilowatt up to 200 kilowatt, very large motors. So over a wide range of operation of induction motor, we get a very low specific power, that is power per kilogram of motor is very low in this comparison. Similarly, the switch reluctance motor and brushless DC motor, which are air cooled, we observe that this is slightly darker gray area. This offers marginally better specific power rating per kilowatt of motor, and but although it is offering us marginally better specific power rating, but it is limited to a limited range of motor output, maybe up to something like a 5 kilowatt, from 0.1 kilowatt to 5 kilowatt. And the overall best specific power is available with the water or oil cooled brushless DC motor, and we observe that this motor offers specific power in the range of 0.5 kilowatt per kg all the way up to 10 kilowatt per kg. So this is a wide range, and so also if you observe the power rating here, the specific power increases with the size of the motor, and specific power decreases with the size of the motor. So this BLDC motor, which is providing higher specific power per kilowatt, this is the most preferred motor with water or oil cooling, because it improves the performance of the motor, and we can use a smaller size, smaller weight motor for the EV, and get the extended range for the same power rating. Similarly, now right hand side you can see there is one table here. It is representing the characteristics of a 37 kilowatt induction motor from the same manufacturer, but for different speeds and for 50 Hz AC supply. So the rating of this induction motor is 37 kilowatt, and it is from the same manufacturer. Observe that the table indicates the speed in one column from 3000 RPM all the way to 750 RPM, and the mass of the motor. We can see that as we move from higher speed to lower speed from 3000 to 750 RPM, the mass of the motor, it changes drastically. It is nearly doubled from 270 kg to 570 kg for the same power rating. Okay, so that is why we observe that the motors which are used in EV application, they have to operate at a very high speed. Then only they will be lighter in weight. Okay, same rating motor, if we prefer a lower speed operation or a lower speed rating, then we'll observe that the weight of the motor will be large, and consequently this will not be preferred uh, in case of EV application. So let us check what are the final thoughts as far as the uh, motor sizing has to do with. Okay, so we'll have to check finally what is it that we would like to do with the motor sizing. So this can be completely explained in the form of a flow. Down here at the bottom you can observe that we are about to choose a motor. So what is the flow and how they are interrelated. Just now we have seen that the motor which has a better cooling, right? The motor which has a better cooling, naturally it will be having lesser losses, and lesser losses means you need to keep a motor having better cooling. It has to be a high power motor. Okay, high power motor, and high power motor we have seen in comparison earlier that higher power rating of motor or higher size, okay, will lead to higher efficiency. Higher power means higher efficiency. We have seen table earlier wherein larger size motor of 90 kilowatt, it was having an efficiency nearly 95%. And naturally high efficiency is possible because of the high speed, right? Higher speed. So motor has to be high power. It will offer high efficiency provided it works at high speed. And naturally when we choose a high speed motor, just now we have seen a table, a high speed motor will essentially mean that the size of the motor, that is its weight, right? So here the meaning of the size is basically it's the specific power, kilowatt output per kilogram. So that will be lesser. Okay, so we just have to now compile this one, and finally the final thoughts are the high power leads to higher efficiency and hence higher specific power. Similarly, high speed leads to high power density. The size of the motor is the most strongly influenced factor by the torque, right, and rather than the power. So we focus more on torque. The consequence is that a higher speed, lower torque motor will be smaller. So we prefer a smaller motor which works at a higher speed and works at lower torque. Lower torque means lower losses. If a low speed rotation is needed, the high speed motor can still be used with a gearbox, and that will be lighter and smaller than the than a low speed motor. So for example, if we are using it in an electric vehicle and naturally we don't want to drive the vehicle in a high speed for every moment of time, so a gearbox can be utilized. But then since it is electric motor, we don't require a complex gear assembly. A simple 1 or 2 gearbox will be sufficient, and the weight of the gear and a smaller motor put together is always lighter than a higher capacity or higher weight motor. Okay, the more efficient motor types, they are like switch reluctance motor and VLDC motor, and they have a higher power density than the induction motor. So this is how we choose the motor size. We realize what are the factors that affect the motor efficiency, right? So high speed, better cooling, smaller size is what is expected.